Hi everyone, this is Mrs. J, and today we're going to be solving rational equation word problems. Alright, so I have two quick warm-up problems for you guys, so please pause the video and give them a try, and then hit play whenever you're ready to check. Alright, go ahead and check your work here. So remember, when we're solving a rational equation, I always like to start by listing our restrictions. So you can see from our denominators that our one restriction here is that x cannot equal 3. And then one way you can solve these problems is by multiplying every single term on both sides by your LCD, which in this case is 2 times x minus 3. So that should eliminate your fractions. So these cancel out, and both factors cancel out here, and then you have an equation that's much easier to solve. So this is a quadratic equation, so you should set your equation equal to 0 by combining like terms, and then we can actually solve this by factoring. So we get two solutions, 0 and 7, and as long as neither of your solutions are one of your excluded values, then they should work, but of course you can always plug them into the original equation to check your answers. And for part B, we have two restrictions, x cannot equal -1 or -4. This one you can solve by cross multiplying, which I did here, and then you're just solving it as a linear equation. So you get x equals -6. All right, so with rational equation problems, there are three really common types of word problems we come across. So one is distance problems, so we'll use that formula distance equals rate times time. So hopefully you're familiar with this formula. Another type is current or wind problems. So this is where you're either flying an airplane or maybe you're paddling a canoe in a river. So there's two different scenarios here. One is if you're going with the wind or downstream. So imagine you're flying an airplane. I'll draw a little airplane right here. So if you're flying with the wind, you're going this direction, the airplane's going this direction, and the wind is going in this direction. So your speed is actually faster because the wind's kind of pushing you forward. So your speed's actually going to be however fast you're going, the airplane is traveling, plus the speed of the wind. And let's say you're traveling, you're paddling in a river. So let's say here's a river like this, and the river is going this way. And here's your little boat or your canoe, and you're going downstream. Again, you're going faster because if you're going the same direction as the river, it's kind of pushing you forward, so your speed is faster. So it's the speed of the boat plus the speed of the river. Now, if you're going against the wind or upstream, here it's important to understand that you're actually going slower. So imagine the same airplane, but now you're going the other direction. So let's say this airplane is facing the other way and you're going against the wind. So you see if you're traveling to the left and the wind's going to the right, it's kind of pushing you backwards. So your overall speed is going to be the speed of the plane minus the speed of the wind. And if you're in this boat and you're traveling upstream, so you're going towards the left here, again, you're kind of fighting against that current. So while you're trying to go to the left, the current is pushing you to the right, so you slow down. So it's the speed of the boat minus the speed of the current. And then the last type of problem that's really common with these equations is work problems. So here we kind of use this basic idea that if a job can be done in t hours, then 1 over t of the job can be done in 1 hour. So to put this with a real number, 'cause it's kind of confusing with t, let's say it takes 5 hours to complete a job. That means in 1 hour, you can finish 1/5 of the job. So we're going to kind of be referring back to this idea. It seems very obvious and simple, but it'll be really useful when we're setting up the equations. Now, of course, there's other types of word problems we will encounter, but these are ones that require a little bit of extra explanation, so I just wanted to talk about them from the beginning. All right, let's have a look at example 1. So it says, Anne and Marie play tennis almost every weekend. So far, Anne has won 12 out of 20 matches. How many matches will Anne have to win in a row to improve her winning percentage to 75%? So we're going to start with this one because it's a pretty basic percentage problem. So remember, the way you can calculate a percentage, like her win percentage as it is you do the number of wins over the total number of matches. So currently, Anne is 12 for 20. So if you do 12 divided by 20, you get 0.6, which translates to a 60% winning average. So we want to know how many matches will Anne have to win in a row to improve her winning percentage to 75%. So let's define a variable. So I'll say that M equals number of matches won in a row. So if she is winning those number of matches, this number is going to increase by M, so it'll be 12 plus M. So now this is how many matches she has won, and not only does the number of matches she's won go up, but the number of matches she's played total will also go up by that same amount. So over 20 plus M. And remember, we want that win percent to be 75. So we have to translate 75 into a decimal, and it would be 0.75. So now all we need to do is solve. So this one, let's multiply both sides by 20 plus M. So this is kind of like cross multiplying. This is going to multiply to the numerator here. This multiplies to the denominator, which is just 1. So it's 12 plus M equals 0.75 times 20 plus M. And now we just need to solve. So we can distribute on the right. 0.75 times 20 is 15. And then we have plus 0.75 M. And then here I will subtract 0.75 M from each side, giving me 0.25 M, because it's 1 minus 0.75. And then I'll subtract 12 to the other side, so it equals 3. And then if you divide both sides by 0.25, you get M equals 12. So she would need to win 12 matches in a row to increase her winning percentage to 75%. And we can check this pretty easily. So if she wins 12 matches in a row, that means that she is 24 for 32, because again, she wins 12 more, but she's also played 12 more matches. So the total of number of matches also goes up by 12. And 24 over 32 is 0.75, which is 75%. So we're all set. So again, this is kind of just a more basic percentage problem, but it is technically a rational equation word problem because we do have this rational expression on the left. All right, let's try another example together. In a canoe race, a team paddles downstream 480 meters in 60 seconds. The same team makes the same trip upstream in 80 seconds. Find the team's rate in still water and the rate of the current. So here you can see that the time it takes for them to travel downstream is faster than the time it takes for them to travel upstream. So we're finding two things. We're finding the team's rate in still water. So that would just be the rate of the canoe. And then we're also trying to find the rate of the current. So we're trying to find how fast the stream is flowing. So let's pick some variables. So let's say that X is the team's rate in still water. And let's say that Y is the rate of the current. So here we can solve this problem by setting up a basic distance equals rate times time equation. So we're going to actually need to set up two different equations. We need to set up an equation that describes when the team is paddling downstream. So they're paddling with the current, so they're going faster, and an equation for when they are traveling upstream. So when they're traveling downstream, it says that they are traveling 480 meters. So that's the distance. 480 equals. Now describing the rate is where we just have to be a little bit careful. So remember when we're paddling downstream, we're going faster. So we actually do the rate of the canoe. So x, and then the current is actually making you go faster. So the rate is actually x plus y. So remember we're traveling with the current. So it's the speed of the vessel alone plus the speed of the water. And then the time, they say, is 60 seconds. So equals 60. And now we can do the same thing for an upstream equation. So it says that they make the same trip upstream, so implying that it's the same distance. So 480 again here. But this time their rate is slower because, again, they're going upstream. So their overall rate is going to be the rate of the team paddling. And then they're working against the current, so it's going to be minus y. And this time the time is 80 because it takes them 80 seconds. So with this set of information, we can actually solve this as a system of equations. So first thing I'm going to do for each equation, I'm just going to move these numbers to the other side using division. So here I'm going to divide both sides by 60, and that gives me 8 equals x plus y. And here I'll divide both sides by 80, and that gives me 6 equals x minus y. And here's a little review on solving systems of equations. We can use the elimination method here. So if we add vertically, we have this really nice scenario, which is ideal for us, where we have the same variable with opposite coefficients, so positive x or positive y and negative y, so they will eliminate. So if we add vertically, we get 14 equals 2x, so x equals 7. So now that we know what x is equal to, we can substitute it back into either of our equations, either one up here. So I'll substitute it here. So 6 equals 7 minus y, so y equals 1. So now if we go back and we look at how we define x and y, x is the team's rate, so we can say the team's rate is 7 meters per second, and y is the rate of the current, so the current is traveling at 1 meter per second. And there you have it. All right, let's try another example together. So here it says Tom can mow a lawn in 4 hours. Jerry can mow the same lawn in 3 hours. How long would it take both of them to work together with 2 lawnmowers to mow the lawn? So since they're asking how long would it take both of them to mow the lawn, that's how I'll define our variables. So let's say t equals the time working together, and that is going to be in hours. So we're going to be using that idea we talked about earlier, that if it takes t hours to do something, you can finish 1 over t of the job in 1 hour. So let's make an equation that describes how much can be done in 1 hour. So we'll think of it like this. Now we're going to find a way to describe how much Tom can do in 1 hour, and then we'll describe how much Jerry can do in 1 hour, and then how much they can do in 1 hour together. So if it takes Tom 4 hours to mow the lawn by himself, he can finish 1/4 of the job in 1 hour. And if it takes Jerry 3 hours to mow that same lawn, he can finish 1/3 of the job in 1 hour. And if you add those up, it should be the amount of the total job they did working together. So if it takes T hours for them working together, they've finished 1/T of the job working together. So again, here's the Tom portion, here's the Jerry portion, and then here's together, assuming that time is the time it will take them working together. So you can see that this is a rational equation. So we can solve this equation by multiplying everything by our LCD. So if we have 3, 4, and t, our LCD is 12t. So I'm going to go and multiply both sides of our equation, every term, by 12t, and that will clear our fractions. So here, 12 divided by 4 is 3, so we get 3t. Here, 12 divided by 3 is 4, so plus 4t, and then it equals 12. So now we just need to combine like terms and solve. So 7t equals 12, so t equals 12/7. And again, this is going to be in hours. Now, since it is a real world problem, it would probably make more sense to give a decimal approximation just because it's easier to understand in this context. So if you plug this into your calculator, we can round to the nearest tenth. We'll say that it takes approximately 1.7 hours to complete the job if they are working together. All right, here's the last example that we're going to be doing today. So it says, suppose that Laura can paint a fence in 5 hours. If Laura and Justin can paint the fence together in 3 hours, how long would it take for Justin to paint the fence himself? So here our question is, how long would it take for Justin to paint the fence himself? So let's define our variable. I'll say t again equals the time it takes Justin alone. And this is going to be in hours. So we're going to do that same setup. We're going to describe how much can get done in an hour. So there's the amount that Laura can get done in the hour, plus the amount that Justin can get done in 1 hour. And if you add that together, add those two up, it should be the amount that they can get done together in 1 hour. So if it takes Laura 5 hours to paint a fence in 1 hour, she can finish 1/5 of the job. If it takes Justin t hours to paint the fence in 1 hour, he can finish 1/t of the job. And if it takes them 3 hours together, in 1 hour together, they have finished 1/3 of the job. So again, we'll solve this in the same way. We'll multiply both sides by our LCD. If we have 3, 5, and t, our LCD is 15t. So we'll multiply every term on both sides by 15t to eliminate our fractions. So here, 15t divided by 5 is 3t. 15t divided by t is 15. And 15t divided by 3 is 5t. So I will subtract 3t from each side, and then you can divide both sides by 2, and we get 15/2, which again makes much more sense as a fraction. So it takes Justin 7.5 hours working alone. All right, that's all for today's video. Thank you guys for watching.